Hello everybody, today we are going to be discussing this circuit over here. We're going to calculate and sketch the values for V1, V2, V3, V4, and Vout for t equals 0 to 3 milliseconds. Our initial voltage across our capacitor will be 0 volts, and our op-amps are ideal and will be powered by 12 volts, and we can assume that V saturation is 10 volts. We are also given V in 1 and V in 2. This is the graph for V in 1. And this is the graph for V in 2, where each tick mark indicates 0.5 millisecond intervals. From here itself, we can tell that we have a period of 1 millisecond. So the first thing we're going to do is we are going to break this circuit up into 3 separate parts. The first part will include from V in 1, V in 2, all the way up until V1 and V2. So since we know we have ideal op-amps, we can assume we know that the current going into each op-amp is 0 amps. Also, at time t equals, between times t equals 0 to t equals 1, or t equals 0 to t equals 0.5 milliseconds, we know that Vi2 is at 1 volt. So we can have 1 volts going in here. And by the rule of ideal op-amps, we know that the voltage difference between the positive terminal and the negative terminal must be equal to 0. Therefore, we also have 1 volt going in this way. The same holds for V in 1. We know that we have 1 volt, we have negative 1 volts. We have negative 1 volt going in here, so therefore we must also have negative 1 volt going in here. This node will also be negative 1 volt. So here we have 1 volt and negative 1 volt. Therefore, the drop across this resistor will be 2 volts. So now we find out that the current flowing this way is 1 milliamp. The same goes here. We know that we have 2 volts. We know that we have 1 volt over here, and our current flowing this way is 1 milliamps. So we can calculate backwards to find our voltage over here, which will be 2 volts. So we know that we have a 1 volt drop across the resistor. So same goes here. Since we have negative 1 volts at this node, we can multiply that with our current flowing this way, and we get negative 2 volts over here for V1. So we will mark those for V1 as negative 2 volts from 0 to 0.5 seconds. And for V2, we will mark 2 volts for 0 to 0.5 seconds. Now, between t equals 0.5 to t equals 1, we essentially just flip our outputs because we notice that Vi2 suddenly becomes low of negative 1 volts and Vi1 becomes high of 1 volts. So we just flip our circuit, and the same goes. We will now get negative 2 volts over here, and we will now get positive 2 volts. And we will mark that on our graph as positive 2 volts and negative 2 volts. And because V in 1 and V in 2 continue to flip until t approaches infinity, our graph will essentially keep flipping for V1 and V2 as time goes on. Now let's look at part 2. Part 2 will be broken up from V1, V2, all the way up until node V3. So the first thing that we must notice is that we once again have an ideal op-amp. So the current going in through this node and in through this node will be 0 amps. We also know that the voltage across here and here, the difference must be 0. So let's assume we will now begin to look at V1 and V2. So let's look at the graphs of V1 and V2. So when we first start out between 0 and 0.5, V1 is negative 2 volts and V2 is 2 volts. So we can say we have negative 2 volts coming in here and we have 2 volts coming in here. However, we don't know what current flows across here. We do, however, know that there is a ground connected here. So all the current that flows in must flow down this way. And because we have identical resistors, we know that the voltage drop across each resistor must be equivalent to the other. So if we have 2 volts here, we will have a 1 volt drop here and a 1 volt drop here. And then we will have ground here. So therefore, we can find the current flowing this way. And because we also know that we have 1 volt here, we must have a voltage difference of 0 across these nodes. We also know that we have 1 volt here. By this logic, we can say 1 volt minus our negative 2 volts divided by our resistor gives us negative 3 milliamps for t equals 0 to 0.5. And now we know that between here and here, we have a negative 3 milliamp current. So we can therefore find the voltage across this, and our V3 is now equivalent to 4 volts. Once again, similar to the last problem, our V1 and V2 will continue to flip from t equals 0 to t equals infinity. So therefore, we also know that our V3 will continue to flip. So we will have 4 volts when we start between t equals 0 to 0.5, and negative 4 volts between 0.5 to 1. And it'll flip continuously and so on. Let us note that since Vn, or V1 and V2 were 2 volts, we have now amplified our signal by a factor of 2. We now have 4 volts and negative 4 volts, which continue to flip back and forth. Now the last section of our circuit will consist of points V4 to V out. So we know that our gate does not close until t equals 1 millisecond. So for anything less than t equals 1 millisecond, the voltage at V4 is 0 because we have an open circuit. So we can mark it as 0. We also know that once the gate closes, V3 and V4 are going to be the same exact voltage. So therefore, we can essentially just copy over the same graph from t equals 1 to t equals infinity for V4. So we have positive 4, negative 4, positive 4, negative 4, and so on and thereforth. Another reason why V4 must be equivalent to 0 before t equals 1 is because our capacitor is completely discharged at that point. So therefore, there's no current flowing through the circuit. There can be no voltage across any of these elements. Now the trickiest part of this circuit is to find our graph for V out. So we will first start by simplifying this last part of our circuit a little bit further. We see that this resistor and this capacitor are in parallel, so let's find their Z equivalent. Z equivalent of a capacitor in parallel with a resistor. Our capacitor 1 over j omega c times R2 over 1 over j omega c plus R2, which gives us a simplified equation of R2 over 1 plus j omega 1 R2 times C. We also know that there needs to exist a current across here. So we have 0 volts here, and we have 4 volts for when t equals time 1 to 1.5 seconds. And we also know that that's equivalent to V out minus 0 volts over our Z equivalent that we just calculated above. Now let's find the omega. We know that T equals 1 over F, which is our frequency. Omega is equal to 2 pi over T, which is equal to 2 pi times our frequency. We know that we have T equal to 1 millisecond, which is equal to 1 over F. So therefore, F is equal to 1 kilohertz. And our omega is now equal to 2000 hertz. We can now find our transfer function, which is equal to V out over V in. Or in this case, V out over V4. V out over V4 is equivalent to Z equivalent over R1, which we can now write as negative R2 over R1 plus over 1 plus j omega R2 times C. We see that this form looks much like an integrator op-amp, which is in the form of A over j omega. So we now know that we have to integrate our signal in order to find our output. So therefore, here we have our actual calculation, which comes out to looking like this. We now have a triangular signal for V out with the amplitude of absolute value of 10 plus 1 over 2 pi j. Thank you for watching.